Alright, so this video is on the binomial expansion and Pascal's triangle. So when we talk about binomials, what we're actually referring to is just two terms. Specifically, these are either added or subtracted. For example, what we would say is that, let's just list two examples here. So simply put, x plus y is an example of a binomial, or even something like x to the fourth power plus 1 over z to the third power, anything like that. Or even simply just like something like m plus n. It can be technically any variable or any two numbers that are added or subtracted like this that specifically make a binomial. Now, what are we talking about when we say expansion? What are we doing when we expand a binomial? Well, suppose we have x plus 3 cubed. Then this expansion technically just means if we have x plus y cubed, that's just writing it out 3 times multiplied together. So x plus y times x plus y times x plus y. And bracket. And then what we would do is we would multiply these through. So we would technically FOIL, because we would do, if we were to compare it to this, we would say, okay, so then the x is going to multiply to here, and then the y, and then we do the same thing in the next two terms. That's exactly what we'd be doing. We just expand all the way through and then collect like terms. But for this case, that's going to be a lot of work, especially as that exponent raises, or as the number here gets higher, we're going to have even more sets of brackets, which means our expansion gets very, very large really quickly. So instead, what we want to resort to is something called the binomial theorem, but we're going to start with dealing with the Pascal's triangle here. So Pascal's triangle is basically just a general term expansion for the base trivial case of x plus y to some power. And this is going to explain what's happening, the pattern we need to look for when we're talking about binomial expansions of technically any kind. So when we're looking at a binomial expansion, we start with, of course, the binomial to the power of 0. So that's just going to be it written out a singular time, right? But this case, anything to the power of 0 just gives us 1. So anything to this power of 0 is just going to give us 1. It doesn't matter if it was like x to the 0 or y to the 0 or even 1 to the 0. Anything to the power of 0, these are all equal to just 1. Then we go to our next line and we say, okay, so now it's x plus y to the power of 1. That just means it's written out one time. This binomial is just singularly x plus y. And of course, we have that right here. It's just a singular x plus a singular y. And then there's the same thing. We go down here and now we have a power to the 2. That means what we're going to do is we're going to expand x plus y and x plus y. And then simplified will give us this. Now let's pay attention to the indice here, or whatever the n value is. So specifically these numbers up here, which is our exponent. What is the pattern as we go down an exponent? What's happening to our expansion? Well, what we're going to notice is that when we have a 0, we have one term here. And then when we have 1 as the exponent, we get 2 terms. And similarly, then we have 2 as our n value, and we get 3. Do we see the pattern here? As the number n increases, so as our number n increases, we see that the number of terms increases by 1 in comparison to the n. So whatever n value is, its expansion has one more term. Let's confirm this with a final line here. If we have 3 in our index or in our exponent, and then we say, how many terms do we have? Well, we should have 4 because it's 1 bigger than that n term. 1, 2, 3, 4. And let's do a last confirmation here on the last line here, where we say x plus y to the power of 4, where n equals 4, we should have 5 terms. Let's confirm this. 1, 2, 3, 4, 5. Perfect. So whatever the n value is, there's one more term than that n value in the expansion. And finally, one other point to note. This is why it's going to be important to reference this as a triangle, as we can see not only does it literally form a triangle, so we can form this triangle out like this. Do we see how as the index grows, or as the n value or the exponent grows, we're getting more terms along the line. So it's obviously going to have a bigger base each line we expand, or for every value we go up. But the other important trend to notice is that the number below, so in this case, let's consider the number 3 in this fourth line here. What's going on here? Well, that's actually saying it's the sum of the two that are directly above it. So 1 plus 2 is equal to 3. Let's confirm this with another line. Let's say we go down to this 4 that's down on the bottom. So we'll say, let's consider this 4. Well, the sum of the two that are directly above it should equal 4. 1, 2, 3 plus 1 is going to be equal to our 4. And you could do that anywhere through the triangle. Whatever two are above should immediately equal the number below when they're added. The last trend to take care of here, or the last pattern we should notice, is that each term within the indice, or within the expansion, I should say, should have the degree of the end value. So what I mean by this is that each term should have that same degree as the end value. So we have, if the degree is 1 in this second line, then x to the power of 1, yes, it is a single degree. And same with here. This has a power of 1, so it matches the exponent here, or the degree of that exponent. Let's go to the fourth line here with to the power of 3. Each of these should have a combined total degree of 3, because we want to match up to this value. So right away, we can confirm in the first one, of course, yeah, x to the power of 3, that's a third degree, so check mark there. What about our second one? Well, we have x to the power of 2 and y to the power of 1. The combined sum of those degrees is 3, so check mark, we're good to go there. And then similarly, we have x to the power of 1 and y to the power of 2. That combined power, or the combined degree, is 3, so that matches up to 3. And then finally, with our last one, we just have y to the power of 3, so of course, that's just going to match the degree of that. And then just one more time, on the bottom row here, consider x plus y to the power of 4. Each of them should be 4 summed up, or either individually. So x to the power of 4, that's a degree of 4. X to the power of 3 and y to the power of 1, yep, that's a power to the 4. We have x to the power of 2 and y to the power of 2, the combined sum is 4. X to the power of 1 and y to the power of 3, that's a combined sum of 4. And similarly, on this last one, we have y to the power of 4. We just know that's a degree of 4, so it matches up to our end value here. Okay, and then now that we've done a deep dive on all the trends of what's happening in Pascal's triangle and how it's specifically constructed, let's consider actually what's going on within each individual line of Pascal's triangle, or what's happening when we expand a binomial. Well, first of all, those coefficients we were getting, so the 1s, the 3s, and the 4s, those types of numbers come from the choose function. So the choose function is actually what constructs that specific term. And we list the choose function, we list n choose k, which is equal to n choose k in this notation. We would say that's equal to n factorial over k factorial times n minus k factorial. And that's what's going to be the part that's dictating whatever that coefficient is, depending on what our n and our k values are for a given term. The next thing we should note about binomial theorem is the fact that when we go from left to right, what's happening with these terms? Well, we have in a binomial, of course, there's two terms going on. So in this case, we have x's and y's. Well, let's look at what's happening to x and y as we go left for right. We originally start with nx, so or x to the power of n, which is the maximum amount of x's that could be here. So we know x's are a maximum, but y's don't exist, or they're not here yet. And then as we go down, we start seeing that we subtract off of our n value, so we're minusing 1 off of our x power or exponent, and then we're listing y with now a power of 1. And then we go to the next one and we say, now we're subtracting 2, but 2 is in the power of the second term in our binomial. So we go all the way to our what we call our general term, and our general term is actually listed as this one right here. We call this the general term because it can locate any term within a given binomial expansion. So I'm going to list this as the general term. Last but not least, we have our n term here, which is just n choose n, which is just going to give us 1 back, because let's say that's 9 choose 9 or 7 choose 7. there's only one way to do that. So this is automatically typically going to become 1. And then we have our maximum y value at the end because it's y to the nth power, meaning that there's no x's but all n's. So to really emphasize this pattern, we have the maximum amount of y's at the end part, but no x's. And then in the beginning of our binomial, we have the maximum amount of x terms and no y's there. As we go left to right, we're seeing that they're alternating. So the x's are decreasing while the y's are increasing. And this doesn't matter if it's x's or y's or whatever the terms are within the binomial, this same pattern is going to hold. And you're going to see that in the examples we do. Consider the following example here. We have an example where x plus 3 to the power of 4. So we want the binomial expansion using our binomial theorem of this line, specifically when the power is 4. So let's identify what our first two terms are. So our one term in our binomial is an x. So we would call this our first term of the binomial. And then we have a 3, which is our second term in the binomial. Last thing we need to point out is that the n value is actually just equal to 4. So n is equal to 4. So now that we have our first and our second term of our binomial and the n value, we can actually just perform the binomial expansion using binomial theorem. So the binomial theorem states that we have 4, or n, choose 0, with x to the power of n, which is in this case just 4, plus we have now 4 choose 1, and that's going to be where x is to the power of 4 minus 1, with now 3 being to the power of 1. Do you see how now we're adding a 3 in here? So we're adding our second binomial term, but we have to subtract 1 off of our first binomial term. And then we're going to add, again, we're going to go 4, choose 2, with x to the power of 4 minus 2, with now 3 to the power of 2. So just to emphasize again, the k value should appear in 3 spots here. And then we have to go plus 4, choose 3, with x to the power of 4 minus 3, with 3 being to the power of 3, plus 4, choose 4. So now we've maximized the amount of times we can choose here. We say x to the power of 4 minus 4, with 3 to the power of 4. And now all we have to do is simplify this. So let's start with our first term. Our first term says that we have 4 choose 0 to the x to the power of 4. Well, 4 choose 0, if you type that into your calculator, it's going to be 1 times x to the power of 4 plus, what's 4 choose 1? Well, 4 choose 1 is just 4. We have x to the power of 4 minus 1, which is x cubed, and 3 to the power of 1 is just 3. So we're going to keep that in the bracket there. Now we have 4 choose 2. And 4 choose 2 is actually just going to be equal to 6. So we get 6 x to the power of 4 minus 2, which is 2. 3 squared, which is actually just 9, because 3 times 3. And then we get 4 choose 3. 4 choose 3 is just going to be equal to 4. And that's to the times x to the power of 4 minus 3, which is just 1. 3 cubed is just 27. And then last but not least, we have 4 choose 4, which is just 1, times x to the power of 4 minus 4. Well, x to the power of 4 minus 4 is just 0 here. And anything to the power of 0 is just 1. So now we can, instead of saying x to the power of 0, we're just going to say times 1. And then 3 to the power of 4 is going to be equal to 81. Okay, now it's time to simplify this even further, because in some of these lines here, you can see that we have two coefficient numbers. We have a 4 and a 3, 6 and a 9, 4 and a 27, and a 1 and an 81. These can all be multiplied together just to give us a singular coefficient instead of dealing with them separately like this. I mean, you could leave them, but it looks a lot nicer to simplify. So 1 times x to the power of 4, that's just x to the 4, plus 4 times 3 is just 12, times x to the cubed, plus 6 times 9. 6 times 9 is actually just going to be equal to 54, times x squared, plus 4 times 27, that's just going to give us 108, and to times an x, and then we have plus 81. And do we notice how all the powers of the x's are different? And we have a constant term in the end with no x's, this 81. So in fact, we actually just consider this our final solution because there's no much more, we can't do anything more to this. And the last thing I want to note about this problem too, do you see how the pattern of the first binomial is decreasing as we go left to right, and the pattern of the second part of the binomial, aka the 3, is increasing? Okay, so now that we've studied binomial theorem and we've done an example to show kind of what's going on within the theorem, let's actually use that information or use that practice to solve a few problems here. So we have one that says determine the numerical coefficient of the 8th term in the expansion of 1 minus x to the power of 13. Well, in this, what we want to do is, unlike the example we did before, what we need to do is we actually need to convert this to have a positive sign in the middle. So we're actually going to rework this. We're actually going to rework this term here so such that it looks as 1 minus x to the power of 13 is equal to 1 plus negative x to the power of 13. And so we have the exact same thing here. A positive times a negative is just going to give us a negative. So we've maintained the same thing, but in order for binomial theorem to work, what we have to do is we have to say, let's make the middle term a positive, and then we'll put brackets around the negative there. And so how are we going to get the 8th term? Well, this revolves around using what we call the general term when talking about the binomial theorem. The general term states that if we want the term 8 is going to be equal to t7 plus 1, which is going to be equal to 13, which is n, choose 7 with 1 to the power of 13 minus 7 and negative x to the power of 7. And do we see how that k value carried through to all three terms? That should happen every time we're looking for the general term of the expansion. That k value will carry through to those three spots. And so when we calculate this, technically what we're going to get is if we deal with, first of all, the 13 choose 7, 13 choose 7 in your calculator should be equal to 1,716. 1 to the power of 13 minus 7, well, that's just 1 to the power of 6. And then negative x to the power of 7. Well, if we have a negative raised to the power, actually, let's just save that to the next line. We would have 1,716, 1 to the power of any exponent is just going to give us 1 back, so I won't rewrite that because 1 times anything is just going to give it back itself. And then we have negative x to the power of 7. If we have a negative to an odd exponent, that negative will stay. So now we have still a negative x to the 7th power here. And then just doing a slight reordering, we're going to actually pull out that negative in front of the coefficient and say that we have a negative 1,716 and to the x to the power of 7. And then the question said, determine the numerical coefficient. That numerical coefficient is actually just this number out front here. So it's just the negative 1,716 number. That is our 8th term. So we would say that if we were to write this in a word problem, we'd say our coefficient of the 8th term is negative 1,716, period. And that would be your final solution. All right, and then now what we have is we say determine the middle term in the expansion of 2 plus x over 2 to the power of 18. So we have two terms going on here. We have our first one, which is here, our second, which is here, and then our n value is actually equal to 18. And they say determine the middle value of the expansion. So we need the middle term of that given line. Well, the first thing to remember is that the amount of terms within a given line of an expansion is actually one more than the n value. So if we know that n is equal to 18, then it must be that there is actually 19 terms in this given line. In order to find the middle term, we're going to say we have 19 plus 1 over 2, which is going to give us our median. And this is going to be equal to 20 over 2, which is going to be equal to 10. And 10 means it's actually our 10th term, which is congruent to the middle term. When we solve for this, let's use our general term formula and do this again. So we have our general term, or our 10th term, is going to be equal to T9 plus 1, which is going to be equal to, well, we have 18, which is our end value, choose 9 times, and then our first term of our binomial was 2, so it's 2 to the power of 18 minus 9 times our second term, which is of our binomial, which is x over 2 to the power of 9. And yet again, these three k values should all be the same here, or the k value should be the same in these three spots here. When this is simplified, 18 choose 9, that's actually just going to be equal to 48,620. We have 2 to the power of 18 minus 9. 18 minus 9 should just give us 2 to the power of 9. And then x over 2 to the power of 9, well, both of those are going to get powers, so what we can actually do is distribute that to both of these and put powers on both. So it's going to be x to the power of 9 over over 2 to the power of 9. And then now we can actually simplify this and say, hey, look, we see a 2 to the power of 9 in two spots. We see it down here, and then we see it up here. So those actually just cancel because we're having them within the same line, and one's in the numerator and one's in the denominator, so we can cancel those out. And so our final line will look like 48,620 times x to the 9. And thus, when we look at this, what was the question asked for? The question says, what is the middle term in the expansion? Our middle term, or our 10th term, is going to be equal to this 48,620 times x to the power of 9. That's our 10th term, which is, in fact, our middle term. So now we want to consider this problem that says, determine the term with y to the power of 4 in the expansion of y squared minus 2 to the 9. So what we want to do again is we want to rewrite this such that there's a positive in the middle. So y squared plus, in brackets, negative 2 to the power of 9, because we maintain the negative technically, but we put a plus in the middle, so it works for the binomial theorem. And then what we want to do is actually just write out a general term clause, because we're actually saying what term is going to give us this y to the power of 4. Well, we don't know the specific term yet, so let's just write out the formula of tk plus 1, which is our general term formula, is equal to n choose k times our first term within our binomial is y squared. And then that's going to be to the power of 9 minus k times our second one was negative 2. And then it has to be to the power of k here. Now let's hyperfocus on this part here, because this is going to be the piece that tells us what number we need, or what specific term will give us this y to the power of 4, because we need this part in the blue circle here. This has to give us a number, or the k value has to be such that we get a total of y to the power of 4. And so what would give us that? Well, let's consider what we need in that exponent such that we can make this expand to 4. So y squared needs to be to the power of 2 in order to make y to the power of 4. Thus, we need to say 9 minus k has to equal 2 in order to make this work. And let's redistribute here. So we're going to plus the k over, plus k over. Our next line is going to be 9 is equal to 2 plus k. Now we're going to subtract our 2 over to both sides. And thus our line will be 7 is equal to k. So now we know our k value. So that's a really important piece of data here. Our k value is going to be equal to 7. Thus, let's use our formula here, and now let's go back to where we were with our general term. It's going to be t7 plus 1 is equal to, well, n was 9, choose 7, which is k, of y squared with 9 minus 7 times negative 2 to the 7th. Then when we simplify this, we say, well, 9 choose 7 is just going to be equal to 36. Y squared to the power of 9 minus 7 is just that y4 term we were looking for. And then negative 2 to the power of 7, that's just going to give us negative 128, because anything to the odd power is just going to maintain that negative. Thus, when we simplify here, we're going to combine our two coefficient terms. And this is going to give us negative 4,608 y to the power of 4, which is the term specifically with that y to the 4. And then when we go to our question, it says determine the term with y to the 4 in the expansion of this binomial. Well, the term is actually just going to be the 8th term, because we know from general term formula, if t7 plus 1, if 7 is the k, then we know this is actually term 8, because it's going to be, k is always going to be 1 less than whatever our actual term number is. And thus we have the term with y to the power of 4 is going to be our term 8.